Thank you very much, Adam. This talk is I'm a deep learning person, right? This talk will mainly be about reinforcement learning, but I view myself as doing reinforcement learning. I'm not necessarily a reinforcement learning person, so if you have penetrating reinforcement learning questions, go easy on me. But the ideas that I've seen come up in reinforcement learning are things that come up in other forms of learning. And that's one of the things about being what I call a deep learning generalist, as I see myself, is this, and it's getting harder and harder to be one of those, is that we really, you can take ideas and insights from one area and apply them to other areas and see what happens. And sometimes interesting things happen. And I think today's story that I'm going to tell you about is an instance of that. I just lost one of my screens, but it'll come back. So I guess let's get started with where I come from. And by the way, if you read my title here, it occurred to me that, I guess yesterday when I was rereading these slides, that it's actually a bit of a tautology. Anyone that really knows this field of RL, this is going to be kind of a self-evident statement that it is in fact training in the face of changing data distribution. This is really, rest assured, this is my starting point. It's not actually my ending point here, so I'm not going to try to argue that this is true so much as sort of guide you through this. But really we're interested in what are the consequences of that. And we're going to talk about what we can do to maybe enable better learning in the face of that kind of distribution change. So a little bit more on my background, and maybe one of the reasons why I'm not, I guess, panicking about the field is that I really do think that there is a lot of things that we don't know how to do well yet. And in particular, we're not very good at out-of-distribution generalization and what I call systematic generalization. So systematic generalization is not a particularly common term, so I've got a definition here for you. It is essentially generalization to examples that may not be drawn from the same distribution as the training data, but essentially shares the same structure, right? So we're not being focused on the distribution of the examples, but we're interested in learning about the structure that's inherent in the data. And there's a little graphic here that kind of describes the difference between them, or at least as I see that difference. Now, I'm not the first one to describe this. In fact, this idea of worrying about systematic generalization actually goes back decades, but in kind of the modern deep learning era, it was kind of reignited by this paper by Lake and Baroni, where they asked the question, do neural nets generalize systematically? And in fact, so for example, when we talk about what we mean by systematic generalization, I think this example from that paper is actually a good one. So if you've just learned the word to DAX, and I ask you, do you understand the meaning of to DAX twice and then DAX again, and you are otherwise an agent that understands English, you would be able to understand what I mean by that. It's a combination of known words with this novel word that you've just used. And it'll be a novel sequence of words, but you can combine them to arrive at this novel meaning. So you can call this compositional generalization if you like. I tend to look at a slightly wider scope and call this systematic generalization. But in their work, their answer was essentially systematically that no, in fact, neural nets do not generalize systematically. I think there's a little bit of nuance to that question, and if you want to ask about this specific thing later on, in the questions, I'd be happy to talk more about this. There's also questions of whether or not scale can actually achieve this kind of systematic generalization. And I think the answer there is not necessarily straightforward one way or the other. This will not be the focus of my talk. Instead, I'm going to talk about something that actually came out of CogSci, and this thing is a method called iterative learning. So iterative learning was a method, or really a hypothesis, for how human language came to be compositional. And so the idea here is that human language emerged through a process of learning and relearning generation from generation. And that process of relearning and the pressure that puts on a language is actually the process that gave rise to this compositional structure of language. So in this case, the remarkable thing about this theory is that it can actually be tested in the lab. So we can take, for example, a set of individuals, a set of participants in a lab experiment, and give them a set of objects that have a shape, a color, and a particular movement pattern, and give them random pronounceable names. This is the set of names we have here beside the objects themselves. And we can let a single first participant learn from a subset of these objects, and then ask them to try to provide a name for all of the complete objects in the set. And then we can take that naming system that this first participant just provided and provide that to a second participant and have them then generate a list of the names of the objects. And we can do this over and over again while this agent is while these set of agents are essentially evolving a language on these things. And what we find at the end is that the naming system that emerged from this process of learning and relearning is perfectly compositional in this case. In real life experiments, it's not necessarily always perfectly compositional, but there's a robust trend towards compositional structure. So in this case, for example, there's a single syllable that dictates the color, then another symbol that dictates the shape, and another symbol that dictates the movement pattern. Syllable, sorry. So this is essentially a really interesting structure. And the remarkable thing about this, from my point of view, is that we were actually able to take this kind of mechanism, this iterated learning mechanism, and apply it broadly in the context of neural network training. So we can apply this iterated learning process and see how the language emergence in neural networks can actually become more compositional. So it's one of these rare cases where a theory from cog-sci is actually robustly applicable to neural network learning. I find that very interesting. It seems to me that it's getting at something deep about the inductive biases of learning these systems. So one of the issues that comes up when we apply these methods, and we have applied these, for example, we tried applying this to a visual question answering task and found that we could actually do better systematic generalization when we apply this iterated learning procedure. Now the question comes up here is that this process of iterated learning, is relearning and relearning, actually is quite laborious. And because it involves having a teacher-student kind of network relationship where you're collecting data from the teacher to train the student, it's difficult to imagine scaling these methods up. So we went in search of streamlining this process while still trying to capture the basic mechanism of this. And we arrived at this paper we called a little bit play on the notion of catastrophic forgetting. We called this fortuitous forgetting in connectionist networks. And this is really work led by my student with Hugo Larachelle, Hadi. And what we found with this work is we could capture most of the benefit we see in iterated learning from just simple resets, but applied specifically to certain parts of the network. And the advantages we see with this kind of work is that in the case of say, for example, in prediction of simple vision tasks, that we're able to generalize much stronger when we apply these kinds of iterative resetting processes. And the key point about this work was that there has to be something. We can't just clearly reset everything and then just start learning again, right? Because that should just be clear to you that all you're doing is restarting the learning process and nothing has changed. So you always have to identify something that remains through the learning process and then resetting something else. And this is going to be a theme that comes up a couple times in my talk. And so I'm not going to actually go into much detail about this work, only to point out that this notion of resetting really started with this paper for us. What I'm going to talk about is how we then applied this work in this paper led by my student Evgeny and co-supervised by my colleague Pierre-Luc Bacon and some other students of ours in this paper, The Primacy Bias in Deep RL. So this is kind of where we're really going to start the content of this talk. But the basic idea here is essentially what happens when we think about applying these resets, this notion of a reset in the context of reinforcement learning. So to get started, we're going to start a bit gently in the context of reinforcement learning. Imagine we have this simple grid world, and we have a discount factor. In this case, I wrote down 0.9. We have 4 actions, up, down, left, right. And the goal here is, if you want to maximize your reward or cumulative reward, then in this kind of a problem, it comes down to just finding the fastest path towards a goal state. So from here, the optimal policy is pretty straightforward. We can write this down. It looks like this, where you see, for example, from a particular action, what's shown is the optimal set of actions to take. When you see multiple actions, that just means that it's indifferent in that state. It can take any one of those actions, and it's equally good. Of course, we can think about the policy evaluation by computing a value function, which is written down here, and a Q function, which we write down here. But the critical thing here that I want to point out is that when we're training these models, of course, we don't know the optimal policy, right? We don't have this information. What the agent sees is this, right? It doesn't have value function, it doesn't have a Q function yet, or at least useful estimates, and it doesn't know what the policy is. It has to evolve this through the course of learning. And what that means is exactly that we have, in the course of reinforcement learning training, something that is fundamentally different than what we have with unsupervised learning or supervised learning, which is to say we're creating a non-stationary process on which we're learning. So we have this interaction between an agent that interacts with the environment to collect data and a model that trains on that data to produce a new agent. Oh yeah, I forgot to mention before we get there, I just want to make clear that the kind of reinforcement I'm going to be focused on is in this context of what we consider off-policy methods, in the sense that we're going to really consider this two-stage process, right? One where we're actually going to be collecting data, interacting in an environment and collecting data in a replay buffer, and then we're going to be in sort of a secondary phase, we're going to be actually learning either a Q function, a policy model, or both on that data. So we're really considering this two-phase process. And this is not true of all RL algorithms, but it will be true for the models that we're considering here. Now back to this non-stationary process that we're creating. So it really is an interaction between these two phases, right? And the key thing to sort of, the key insight for us anyway, was to realize that this is actually a series, this is creating this series of out-of-distribution generalization problems. Right? Which from our point of view was interesting, because now this is something we've been working on for quite some time with this iterative learning process, with the set of resets. We actually have been working on out-of-distribution generalization problems for a while. And so we were interested in seeing what happens when we apply these resets in the context of this kind of reinforcement learning problem. The other thing to note that will become important for us a little bit later is that there is actually also in this iterative process, this non-stationary learning process that we see in RL, there is a process of loss of plasticity that comes in. Which is to say, after a while, after your network has been trained and trained and trained, we know this about neural nets, and in the case that I'll be describing, all of our models you can assume them to always be neural nets. We know that after a while, these methods, after a sufficient number of updates, learning becomes difficult, meaning that these kind of gradient-based updates tend not to lead to the same kind of movement in parameter space and equivalently in function space as when we see earlier in training. Right? So this kind of loss of plasticity builds in. And so we're asking the question, well, what happens if you actually try to just use resets to train this kind of method? So specifically what we're going to do is periodically reinitialize the parameters of our neural net, and at least the last few layers. We're going to see in some cases we actually are very aggressive and reset all model parameters. And in other cases, we're only going to be resetting the last few layers. But in every case, we're resetting at least the last few layers. But the critical thing, and what gets preserved, is the replay buffer. Right? So this is really critical for us. We're learning these agents, and we're actually just pretty aggressively resetting these model parameters. But the replay buffer remains, and we're going to be retraining these agents on the existing replay buffer. That's the thing that's constant throughout training, that buildup of that replay buffer of experience. And the thing that was surprising to us was how this replay buffer essentially acts like a non-parametric representation of your policy. This was an interesting insight for us that we didn't know before we tried this kind of thing. So the setting that we're going to be looking at here are, we're really interested in the data efficient regime here. So we're going to be looking at, for example, DeepMind control and Atari. Specifically for Atari, we're looking at the 100K benchmark. So this is 100,000 steps in the environment on 26 of the Atari games. This is kind of a standard benchmark. It's not a loved benchmark, but I think it was pretty useful for us. And the thing that's interesting for us is that this 100K benchmark essentially amounts to, say, 2 to 3 hours of direct experience with this game, with each of these games per game. So this will be interesting when we sort of push this idea a little bit further on later in this talk. And in these two different kinds of environments, these two sets of environments, we're going to be applying a few different methods that are known to be data efficient. We're going to be applying soft actor critic to the dense deep mind control environments. Dense here meaning the state is dense. We're representing these joint angles. We're going to be using and comparing DRQ, and this is a case where it's basically it's SAC with data augmentation. We're applying this in pixel space, and we're going to be using something we've developed, SPR, which is essentially a self-supervised learning method that predicts future state representations. And it's essentially, a fairly high-performing benchmark on top in the Atari regime. So DRQ and SAC are going to be on the DeepMind control, and we're going to be applying SPR in Atari. So anytime you see SPR results, this is going to be on Atari, and specifically the 100K benchmark. All right, so how does this work? If we just apply resets, and I want to emphasize, we're not changing the basic algorithm here. We will be modifying the hyperparameters slightly, more on that as we go along, but essentially we're really just adding these resets to the model. We're not changing the basic algorithm. And what we can see here in the case of Atari, a significant improvement in performance when we look at SPR plus resets over SPR. And this is sort of a grab bag of the high-performing methods on this particular environment, the data-efficient Atari environment here. And so this was initially quite surprising to us that we'd see such a benefit to this kind of just simple procedure, just adding these resets to the model. The other thing, if we try it on with SAC or soft actor critic, so yes here just means that we are applying these resets. No just means that is the same basic model without resets. And we see a significant improvement in performance there. Same story with DRQ, a significant improvement when we apply those resets. So I wanted to show you just what that looks like, what these resets look like, just to kind of convince you that we are in fact fully resetting. And this is a case where we're applying this to DRQ, where we are fully resetting the policy parameters, all of the policy parameters of our policy neural net, and the value function parameters. And the only thing being preserved is the replay buffer. And the thing that was surprising to us, and so you can see in the orange line here, these are the reset models. And the critical thing here is just how, first of all, how dramatic it is, right? We're just kind of doing this shot down, right? It goes right down in performance, which is, we're learning over again, so that's not too surprising. But what is surprising, perhaps, at least it was for us when we first saw this, is how quickly it recovers, right? And this is because we're preserving that replay buffer, right? These models, it turns out, learns very quickly from a replay buffer that has a lot of useful data in it. And so on the left here, we see the hopper-hop case where actually the resets don't actually help that much. They don't hurt, but compared to just standard DRQ, there isn't much of a difference. On the right, though, for the quadruped walk environment, we actually do see a pretty big difference, right? The standard DRQ isn't really getting off the ground, in this case, probably quite literally. Whereas for the DRQ plus resets, it's actually able to bootstrap up useful policies and being able to reset. So one of the questions you might be asking yourselves, and which we asked ourselves too, is, well, why? Like, what's going on here? What are these resets doing? And at this point, there's essentially two hypotheses, but the main thing I want you to come away with is I actually don't know really why these resets help. We have a few hypotheses, and I can show you a little bit of evidence for them, which I'll show you, but we fundamentally don't know. But one thing I do believe, which is important when I say these are not mutually exclusive, is that I do actually think that there's very likely more than one thing going on here, more than one reason why these resets are helping. And so it's becoming difficult to sort of tease apart why they help. Because in some cases, we can actually replace resets with other things. And in some cases, it works just as well. In other cases, not so much. So we're still very much in the process of trying to figure this out. But the first hypothesis, for what it's worth, is that it's just dealing with this loss of plasticity that I mentioned before. Right, so we're resetting model parameters, we're putting them in this initial parameter space where we know neural nets can learn very effectively, and we're providing it with this replay buffer full of valuable data. It can learn very quickly from there. And that's pretty compelling. I'll show you evidence of that in a second. The other alternative hypothesis is more, I guess, maybe more of a bold claim. Well, to a certain extent, and this is one that I must admit I'm a little bit biased towards, is that, you know, if we just think about where this idea for us came from, our trajectory in getting here, really, we were inspired by these ideas from iterated learning, right? That these resets actually enable better generalization in these models, and that we end up with more robust models, and that better robustness or say better OOD generalization enables better exploration. And this is actually what's giving rise to better models. There's this kind of maybe a more mundane correlate to this, which is this same activity of this kind of resets can also actually help avoid divergence of the Q function estimator. And this is, you can see this as maybe just a little bit more mundane in the sense that if the Q function, usually what we see as a failure point of these methods is the Q function just diverges and then it starts to predict because there's that max in there, it starts to over-predict value. Whereas if you're kind of constantly resetting the model parameters, it's actually difficult for these things to grow that high. So it's kind of a mundane reason for why these work, but that could be an important factor. We do see it in certain instances. So this is an example of where we think loss of plasticity is playing a role. So this is the cart pull swing up example here, where we have, and DRQ in this case, and we're plotting here the critic gradient norms, and we're looking at DRQ against DRQ with resets. And the critical thing here is that in this environment, the reward is sparse, and it only gets rewarded when that pole is swung up to the vertical position, right? So it has to sort of do enough exploration to get it up there. So one might be tempted to think, oh, well, this is just a case where, for whatever reason, DRQ just never gets that pole swung up there, and that's why it never finds that position, and so it never learns a good policy. But we can actually inspect the replay buffer in this case, and here, in both cases, there are those, early on in training especially, there are these examples of non-zero reward. In other words, the early exploration for both the DRQ and DRQ with resets does show these examples of where it was spun up and it gets non-zero reward. The difference is that for whatever reason, the DRQ doesn't seem to be able to take advantage of that kind of data, those non-zero rewards in its replay buffer, whereas once we add resets, it is able to take advantage of those and bootstrap up a better policy. So we view this as evidence towards this loss of plasticity argument. On the other side, this is an example in the Walker-Stand environment, looking at the critic outputs here. This is our Q function, where we essentially have a straightforward case of the critic diverging, predicting very, very large values, whereas our resets are just kind of, you can see quite clearly the resets are not really making that able to happen. So whether or not this is enabling generalization, and that generalization is aiding better resets, or this is just a more mundane of mechanically just forcing this thing down, that is hard to really tease apart. But I think we're actually seeing evidence of both of those kinds of things happening here. Okay, so that was our first work in this space on just the primacy bias. But we kind of tripped on something with these methods, and we actually found that with these resets, they kind of unlocked a different kind of way for these models to work. And in fact, what they did is allowed us to explore different hyperparameter regimes for these same basic algorithms that were not actually possible or did not perform very well without these resets. And one of those is the replay ratio. So the replay ratio, just for those of you that are not aware of this, of what this term means, is it's the number of updates you do on your replay buffer compared to the number of steps you take in your environment. So a replay ratio of 1 means you do 1 gradient update of your model parameters on the replay buffer for every step in the environment you take. Right? Larger replay ratios mean that you take multiple gradient updates for every step in the environment. So there's a question, there's kind of always something when you sort of split this apart. One could imagine that we could be a lot more data efficient if we actually enabled greater replay ratio scaling. That is to say that we actually scale up the number of updates we take per step in the environment. Right? Intuitively, this makes sense because it feels like we could just suck out more information from the data exists if we're taking more gradient updates on that data. But of course, the downside of that is typically, and this actually happens in many settings, is that our data ends up being, quickly overfit, right? Our models quickly overfit on this relatively small amount of data, and this leads to deterioration of performance. But the interesting thing is that our resets seem to counteract that effect. And so this is really the major point of this middle paper that on this point, is that as we increase the replay ratio, and we add this SR here, and it's just think of this as resets. This actually just stands for scaling by resets. It's a little confusing, but you can think of SR SAC as just SAC plus resets. And the same thing with SPR. SR SPR is just SPR plus resets. And in both of these cases, what we're seeing is that as we increase this replay ratio, we're seeing monotonically better performance, or near monotonically better performance across the methods with resets. We're not seeing that at all in the standard methods without these resets. So it's clear that what this really is just, it's the same algorithms, it's just a different hyperparameter, right? This replay ratio is just a hyperparameter. But enabling these resets or introducing these resets has enabled a different kind of hyperparameter regime to do well. And what we're actually seeing also is that we're getting far better performance than we would have otherwise. So we're really able to take advantage of this data in a new way. A few other basic things on this, if we focus more on Atari, we can see that in the case of SPR, that actually in the previous work in the original primacy bias, we were actually, in the case of SPR, we were only really resetting the Q value head. We weren't actually resetting the full SPR convolutional model. But in the case where we've updated we've introduced resets and we're using this higher replay ratio scaling. In fact, actually we find benefits by using what we call soft resets. So not necessarily completely resetting the models of the convolutions, but using shrink and perturb, which is to say we scale those parameters down towards 0 and then add a bit of noise. And another thing that's interesting is we found that beneficial to now introduce an exponential moving average target network here. Previously, we were just using the same network, and we found it didn't actually matter in the original primacy bias paper. But now with this higher replay ratio scaling, we're finding benefits to this target network, using an EMA target network. And in particular, we're actually going to be using this target network for exploration. We're not going to be drawing drawing actions from our online model. We're going to be drawing actions from our target network. And this turns out to be pretty important for performance. So one of the reasons for that is that, this notion of policy churn, so this is a notion that was introduced fairly recently by Shaw et al. In this paper down here, where we're looking at, this is essentially that small changes in the value function can lead to very large changes and quickly, meaning like after a single update of the parameters, large changes in the policy model. And so, and we can see here that the online network is actually, we see very large amounts of churn, which can lead to kind of instability in training. But the target network, this exponential moving average target network, actually has like an order of magnitude less churn. So we think this is one of the reasons why using it for exploration is actually very, very helpful. But again, we're just really talking about, this is just another kind of hyperparameter change that we're looking at to get better performance with the introduction of these resets. And the last thing to note on this point is just that one of the things we found is that one of the benefits we see with resets is it kind of uniformizes the training dynamics. So here we see across a bunch of different replay ratios, For example, I can't even see it from here. The parameter norm and the gradient norm, in this case, on the left and right, respectively. And we can see here that without without the resets, these are quite different. In fact, the parameter norms grow quite large. But in the case of the resets, they're actually quite uniform across these replay ratios. We see the same thing for TD error, which is now shown on the left here. Same thing, that the TD error is quite different across these different replay ratios if you don't use resets, but with resets, they're quite uniform, very much in the same range. So the last thing we did within this kind of line of research of just kind of exploring what can be done with these simple resets so what we've done so far is we've looked at, like, resets do tend to improve performance. We've opened the door to different kinds of hyperparameters and saw that we could do replay ratio scaling, could pretty significantly improve performance. And in this work, we're actually going to, which is kind of our last in this trilogy of works on this topic, we're actually going to be looking at the question of what about network size? Can we, because in reinforcement learning, the size of our networks have been actually quite small compared to the kind of scaling we see in the supervised learning world and in the unsupervised learning world. And it's not because people in reinforcement learning aren't aware of that. It's just that it doesn't actually work very well to scale these things up. And so the question we have is, well, with this new hyperparameter regime that we find ourselves in, are we actually able to do that kind of scale up? And the answer we have is yes. By the way, our method here, bigger, better, faster, I didn't come up with that. It is a bit descriptive, but it's not my favorite. So on the plot here that I'm showing, this BBF method is ours. It stands for bigger, better, faster. But you can see in the plot that, in fact, we are able actually to do quite well. So this entire paper focuses on the data-efficient Atari regime. And we can see that we're actually able to finally beat efficient zero, which is a model-based method, using a simple SPR, which is a model-free method, in conjunction with these resets and a set of new hyperparameter regimes, which we'll talk about. But we are actually doing something else, which, like efficient zero, we're actually matching human performance. I realize now I've neglected to mention what we're measuring here. So IQM stands for interquantile mean. You can think of this as just a robust mean performance over our random runs, or our random training runs. But in the case of Atari, these IQM values are normalized to human performance. So an IQM of 1, which is what we're seeing here, means that we're roughly matching human performance with an amount of data that's roughly equivalent to what the humans had to train on before evaluating what human performance and defining what human performance was. So I think this is a really interesting thing. We are now, with a model-free method, getting to a point where, mind you, we are scaling up compute to achieve this, but we're now at a point where we're actually getting with this sort of matching human performance with a human comparable amount of data, which I think is a very interesting thing in a non-trivial environment, I would say, in the case of Atari. So the question is, how do we achieve this? Well, it basically comes down to considering a different set of hyperparameter regimes. So we had been in a box in the data efficient RL scenario where these hyperparameters worked well for, they did well to learn fast, but they weren't necessarily the best parameters for long-term asymptotic performance. Say, for example, a large n-step return. We were using large n-step returns and low discount rates. And again, these are helpful for learning fast, but they tend to lead to high asymptotic error. And so the first thing we need to do is do away with that. The second thing is we're using small data sets. Which we can typically, because we're in the data efficient regime, that we can't change. But what we can do is perhaps add regularization to help avoid some of this overfitting. And resets play an important role into that. Using maybe perhaps other kinds of regularization are going to be important for that too. And finally, we're using these shallow networks, which just don't tend to generalize very well. So we're actually going to sort of step into and explore more modern, deeper networks in that case. So sort of a sketch of how we actually approach this kind of performance. We're going to use the end step that are more custom for cases where we're actually not worried about the data efficient regime. So we're using n-step return of 3 as opposed to 10. And we're going to use a higher discount value of 0.997. Perhaps you guys are used to saying high discount actually means low discounting, but for me, that's always still a bit of a trip. But so we're actually discounting less when we say we have a high discount value here. And we're going to make use of resets. In fact, we're actually going to use harder resets in the sense that when we use those soft resets on our ConvNet, we're actually going to be scaling those models more aggressively back towards 0. And then perturbing them as opposed to what we were doing before. We're also going to be using weight decay aggressively as well, which turns out to be a really important thing. If you use Atom W, that turns out to be a key difference as well. Atom versus Atom W, weight decay is actually very helpful in many of our RL settings if you use Atom W. And in fact, another thing that turns out to be very important is actually we're going to anneal both of the discount factor and the n-step returns, right? So from the sort of, we're going to start at the sort of data efficient parameter values, and we're going to anneal them towards the non-data efficient standard parameter values for these. And that turns out to actually also be pretty important. So it turns out that those non-data efficient ones are kind of hard to get off the ground, hard to get started learning with. So if you start with the data efficient ones and then anneal them away, we sort of try to get the best of both worlds. And in fact, this was actually suggested in the Kearns and Singh paper from 2000 on tabular TD, and we found it very helpful for us in this setting as well. And finally, we're going to use a ResNet. In fact, we're going to use an Impala. We're going to build off the Impala ResNet here. So taking all of those kinds of things into account, the kind of scaling we can get looks like this. So in blue here is that method that we saw before, right? This is this ResNet or SR-SPR. The plot on the left is for a ResNet, and the plot on the right is just the same, the DQN ConvNet structure. And where we're varying is the width of the model. So number of parameters is essentially the width of each layer in the model. And what we can see is with this set of hyperparameters, we're actually able to take advantage of scaling in the model size in a way that's clearly better than what the kinds of the model configurations we had before. And we're able to, we don't see this here because what we're not showing you is scaling with replay ratio. This is just with the replay ratio of 2. But when we scale replay ratio, we're actually able to break that IQM of 1, that human performance barrier. But here, in both cases, either with the DQN CNN or with the ResNet, the Impala ResNet, we're actually seeing improved performance with model scaling, which is something that we struggled with previously in the context of RL. So if we do our ablation study, we can see that the things that actually turn out to matter quite a bit, the hyperparameters we're most sensitive to are n-step returns, the use of resets, and this annealing. The annealing turns out to be really important to get better performance. Everything else that we've mentioned so far is important, but not nearly as so. Those are the 3 critical aspects. And so finally, on this, we have, we're basically able to beat previous methods with this model-free method here. And the one question you might have is, well, is this benchmark just done, right? Is Atari 100K, the data efficient benchmark just kind of done? And actually, it seems like maybe not. If you look at the plot on the left here, what this is plotting is the fraction of runs with score greater than value tau as a function on the x-axis of different values of tau. So for example, where that dotted line is, if you can see it, that's a tau equal 1. So this is for, again, human normalized performance. So this is the fraction of runs on which we achieve human performance. And you can see that for both efficient 0 and our BBF, the fraction is only around 0.5 of our runs actually achieve human level performance. And you can actually see that where BBF seems to be improving is in doing really, really well, far better than human performance on some small fraction of games. So we still have quite a bit of work on those hard games to do much better. And so I think there's actually still some reason to continue with this benchmark and focusing on those kinds of harder games. So some open questions, open remaining problems for us. We haven't been able to see an equivalent scaling. I showed you a scaling with model width. We haven't been able to show an equivalent kind of scaling benefit with model depth. So really deep ResNets, we're still not able to scale with respect to them. Yeah, so that we don't know how to do yet, unlike what we see with supervised learning and unsupervised learning, right? So that's still not solved. We have, yeah, so if we make progress towards hard exploration tasks, no, we haven't actually made progress in the hard exploration tasks. BBF still gets around, an IQM of 0 for those. Can we transition smoothly from the data efficient regime to the asymptotic regime? For example, can we just be more sample efficient or data efficient, but allowing us to have more and more data? That we haven't explored yet. That's an open question, because we've been really focused on this pretty restrictive data efficient regime. And finally, are we able to get these kinds of benefits without resets, right? So all of this has been based on this idea of resets, but resets are pretty clumsy, right? It's a rather extreme maneuver, and one would hope that we could figure out, enabling better performance without them. So this is actually something we've been working on, putting a lot of our effort in that direction, of how do we get the same kind of performance without these kinds of resets. Sometimes weight decay by itself, aggressive weight decay is enough, but it doesn't tend to be as important as important in every context. So, just check on time. Yeah, so I guess, I think I have enough time. I'd like to wrap up with actually a pretty different setting for where we've applied resets. And this is in the context of language models with alignment. I'll try to go through this rather quickly. This is kind of our most recent efforts in this direction, but I wanted to share it with you because I think it connects with the iterated learning perspective that we started earlier on. And it offers a different kind of context where we could see these kinds of resets being applied. ChatGPT, the rather famous language model that changed a lot of people's perspective, especially in industry, on these kinds of models, starts with just a simple language model, GPT 3.5, on which we apply what's called RLHF, or reinforcement learning with human feedback, to achieve this. And the way this kind of RLHF works is you essentially collect human feedback data. So you have a language model that emits a series of outputs. A human ranks those outputs in terms of their performance. You then have a reward model that you train to match the ranking of those human performance. And then you freeze that reward model, and that's going to be your reward model. And then you're going to do something like reinforcement learning, using that frozen reward model to try to bootstrap up your language model to essentially better align with human preferences. Right. So this is a really interesting idea and one that people have sort of toyed around with for quite a while, but I guess it's only really in the ChatGPT regime when we've hit this kind of scale where we're actually seeing really strong benefits of doing this kind of thing. But there is a problem that comes up with these kinds of RLHF applications. And I'll sort of go through this gradually here. So let's say we have an example like this where we say Shin black ramen is tasty and rich, and right? So we know from our previous data here, collected from our humans, that Shin black ramen is in fact good. So we want anything that says that this is good, a completion that says this is good, is going to have high reward. So this is going to get, a reward of +1. That's good, but we're going to try to do better, right? This is training on this reward function. So with this this reward, this fine tuning using this reward function, we're actually going to see that we can do a little bit better and get maybe Shin Black Ramen is very good, and maybe that's seen as being a little bit better than the original, and so it gets higher reward. Well, it can keep going, and it can go to say, Shin Black Ramen is love, 10 on 10, which is great. It's a very positive output. The trouble is, it's not very fluid from an English point of view, right? So, and this is a real issue that happens with these kinds of reward models. It's solving the task, but it's doing so in a way that kind of deteriorates the original function of the language model. And so this kind of issue is well known in the community that works in this. It goes by a number of different names. Robustness to overfitting is one of the way this problem is described. This problem is known as the alignment tax, overparameterization, and it's also known as reward hacking. And fundamentally, it's this trade-off, right, between what I would call language drift and the reward or performance that you get on this task. And it's how do we balance these two things? And I'm showing you here essentially what is a Pareto frontier graph that shows that you kind of have to, what would be optimal is the thing in the upper right corner of this graph, but it's hard to achieve that. These things are usually a trade-off. And so the question we had is, well, how can we apply resets in this context, and can resets be thought to do better? And there's some reason why we thought that this would actually work, and it comes back to our original use of these of the inspiration of these reset methods in terms of iterated learning, right? So we know that these methods are good at invoking an inductive bias towards compositional structure. Perhaps that would be useful in this context. The issue that comes up is that we end up having, in the case of resets, it's a fundamentally different scenario than we had before, right? These are on policy methods, so we're not using a replay buffer. So we need to come up with a different way of preserving information across these resets. The other thing is we're not resetting our model back to some initial model, right? We're actually resetting the model, or we need to preserve something about the original pre-trained language model that we start our RL fine-tuning with. So this puts us in a rather different regime than we had in our original reset structure. So we needed a novel way to do these kinds of reset. And the way we came up with is what we call elastic resets. And so the idea here is we're just going to introduce an exponential moving average of our online model, and we're going to do a kind of a two-stage, well, it happens simultaneously, in fact, but the reset is going to be, we're going to take our online model, reset it to the EMA, and at the same time, we're going to take our EMA model and reset it back to the pre-trained model. And we're just going to do that periodically, and that's our reset strategy. And we're going to apply this in the case of two applications. One is in this case, which is called the IMDb mock sentiment. And this is actually very similar to the kinds of examples, the running examples I've been showing you for the last few slides. So the idea here is we're going to train a model, a reward model, on IMDb reviews and sentiments, and have our GPT-2 language model pre-trained on IMDb reviews. And so our reward model, our distilled BERT model here, is actually going to be trying to take those reviews and try to predict the sentiment. And then we're just going to treat that as a reward. Okay, so this is a bit weird, right? So this makes this kind of a toyish task. We're just going to treat sentiment as a reward, which means that maximizing reward is just outputting higher and higher sentiments, like more positive sentiments for our model. And that's the idea. So that's exactly what we're going to do here with this model. Our GPT model is just going to do sentence completions and trying to maximize sentiment in the process. And of course, we're going to try to avoid this drift of these sentence completions while we do that. And here, there's a lot going on here. But I think what I'll focus in is the figure on the top left, the top right, which is that Pareto frontier graph, right? So we're looking at perplexity which is kind of an imperfect measure of the drift I was talking about. Here it's actually measured so that perplexity going down is actually, lowering perplexity actually goes up on the graph, and task performance or reward is across the x-axis. So again, we have the top right point as being the optimal value here. And you can see that in this case, if we compare our elastic reset method with PPO and another method that's actually designed to counteract drift, we actually see a significant improvement in performance in the trade-off between high performance and minimizing drift when we use this elastic reset method here. The next setup that we're going to apply this to is the stack llama setting. So here we're actually going to be using the 7 billion parameter llama model as our language model. And we're going to be training this on stack exchange data of questions and answers. And we're actually going to train a reward function that uses the upvotes and downvotes on the answers that users provide as the reward. Right, so this is an established benchmark in this field. We're going to freeze that reward model, and then we're going to fine-tune our llama 7 billion model to actually maximize the reward. Right, so this is exactly, essentially, the setting of our LHF, where we're trying to improve performance on the model, and we're going to compare PPO with our elastic reset method. And here you can see that as we get better and better performance, so we're looking at the extreme right end of our parietal curve, we're seeing that we actually see much better performance while maintaining minimal drift here with using those resets as compared to standard PPO. And I should say, standard PPO here, we're actually still regularizing PPO, which is common. So we're using a Kale divergence regularization back to the original model. So we're actually also trying to use standard methods to combat this kind of drift problem. But we see that our elastic resets is actually more effective than that. So one of the things that's interesting is this human eval thing in the table that's on the right of the table. This is taking an additional set of questions and answers which are code. So this is actually developed by OpenAI researchers where they've said, write me some code that does X, and the model is then tasked to actually generate code, which is actually evaluated to see what it generates and if it gets the right answer or not. So what we're seeing here is actually the percentage of time that model gets the correct answer after multiple runs. And interesting, you can see that there, the elastic reset is actually doing far better than the PPO model. And you can actually, it's an interesting case because you can see the zero shot, that is just the pre-trained model. It actually does very well on that task. And you can see that it's because there's quite a big difference between the fine-tuning distribution that was used here and this evaluation metric. So you can see that the drift that has caused the PPO model has actually hurt the performance on this kind of evaluation significantly, whereas it really hasn't in the case of our elastic resets. So now the question is kind of, well, why does it work in this context? And I just wanted to sort of maybe I'll finish saying that in this case, it doesn't seem likely that you could argue that it is a loss of plasticity. And the reason for that is actually if this kind of reset was countering loss of plasticity, you should expect the opposite results. Because a loss of plasticity, if you suddenly gained plasticity, it should quickly move away from the initial model, right? It shouldn't necessarily resist drift, it should actually accentuate drift. But that's not what we're seeing. So that really can't account for this behavior of this elastic reset model. And actually, in fact, this kind of makes sense also because we are not initializing to a naive model that's in the right regime to learn quickly, right? We're actually initializing back to our pre-trained language model. So whatever loss of plasticity that has, that's going to be there in that model. Finally, there may be two other mutually exclusive hypotheses. You'll see the one that I favor in a second. But first, we can imagine that this reset back to the EMA model essentially allows us to do a kind of a different kind of search in the solution pathway where we're actually finding higher value solutions that are somehow closer to the pre-trained model. The other hypothesis is basically back to this this iterative learning mechanism, that maybe this resetting is just creating an inductive bias towards compositional structure. And that is why we're actually doing better for drift, because it's preserving the structure. When we do this kind of RLHF, the kind of drift we typically see is what I call idiosyncratic, meaning we have a sequence of tokens that will mean something very specific, but kind of what would seem random to a person. It is very non-compositional, because it will be the sequence of tokens that mean something to the other kind of agent, to the reward model, right? You're overfitting that reward model. And that is kind of walking in the opposite direction of having this kind of compositional structure. So I think if we were inducing an inductive bias towards compositionality, that ought to show this kind of benefit. And finally, if I just back up a second, I actually think this pattern of results is supported by the relative improvement of performance on human evaluation for the reset model in comparison to what we see for perplexity. So this perplexity measure, which you can see is better than PPO, but it's not a lot better than PPO. And this is measured relative to the original pre-trained llama model. So we're actually moving the model parameters. The model is actually changing significantly from the original model. It just doesn't seem to be hurting that much. So to me, that suggests that what we're actually capturing is something more about the inductive biases of the data, and not necessarily just preserving the model to be close to the pre-trained llama model. All right, that's it for me. I think that's the end we have. Okay, so thanks.
We just have a few minutes if anyone has questions. There's mics in the middle of each row there, labeled 1, 2, 3, so head on up and someone will cue you on the mic.
I'm wondering if we can do better resetting or more intelligent forgetting. So I wonder, would it be better to reset more important parameters or less important parameters? Like when we want to learn a new thing, we need to forget certain things, and if it's like less relevant to the new task, sometimes helpful, but sometimes also challenging our basic assumptions is also useful. So I wonder which way would be more beneficial.
So in Hadi's paper, which was the first kind of paper that I didn't really go into, that's really where we explored that kind of a question. And there what we found was that one of the things we found is that we tended to, do better if we reset the upper layers of the neural net, where the input is coming in at the bottom and the output is close to the top. If we reset those upper layers, we tended to do better in terms of better generalization performance. That is a very robust result, and it actually is consistent with findings where overfitting tends to happen in those layers. So I think if I was to give someone advice on what they should reset where, like, at least if they want to just do generic generalization, or sort of better generic generalization, reset where you think the overfitting is happening. And that's usually the later layers. Yeah.
Thanks.
No problem.
Mic number 1, please.
Yeah, hi there. Thanks for the great talk. One question I have for you is regarding the reward model and the language drift that you're seeing. I'm wondering if this is almost an artifact of the type of failure to generalize that you're seeing elsewhere, where the reward model itself is allowing you to kind of give these types of outputs that are love 10 out of 10, and like that it's giving you too much reward for these kind of not what the human users actually said that they wanted, but like that's in that space, and that it's allowing that kind of generalization and not saying like, no, I wouldn't say that as a human. Like I'd say, oh yes, it's better, but not love 10 out of 10, maximum supreme.
Yeah, that's exactly right. In fact, this is what we found. So this isn't the first time someone's tried this kind of technique where you learn a reward function, then optimize with respect to it. The problem is that it's exactly this, is that what you quickly do is extrapolate on this reward function, right? So you very quickly veer away from where you have data support, and you go into these regimes where the reward model could go crazy, right? And that's exactly, we're seeing that a little bit in this context. But you know, the more data you have to support that, the better this will do, the more you're able to generalize a little bit better. But one of the things is that it's actually, this is a context where it's not going to be easy to scale up, right? Because you need human feedback for this. So it's not quite like we have just for generic language modeling, where we have lots and lots and lots of data, and scale isn't really an issue. Here, scale could be a real issue. But we still see a benefit if we initialize with a language model and then fine-tune that towards this kind of a reward function. We're able to use it, but it is exactly the problem that you described.
One other piece of, quick follow-up? Yeah, so one other piece of that as well is that the human feedback that you're getting is usually very low dimensional. It's like thumbs up, thumbs down kind of thing, whereas you don't necessarily have that data from them to even be able to express how good this is. It's more of a binary thing. And so being able to craft that model appropriately is, you don't even have anything to build it off of.
Yeah, we sometimes get a slightly better than that in the sense that we can get a ranking over multiple outputs. So it's a little bit more, a little bit higher fidelity than just thumbs up, thumbs down. But yeah, it's a challenge for sure.
Just time for 2 more questions. We'll do number 2 and then 3.
Hi. When I'm doing reinforcement learning, I always feel like a witch with a big cauldron and I'm putting different things in there. Is there a strong theoretically foundation of why resetting works so well?
So first of all, I would say it isn't just reinforcement learning. I would say this is kind of true of the deep learning era that we're in, right? It's almost all deep learning people feel this way, in the sense that we are dealing with models that we don't fully understand. We have principles and we have kind of intuitions, but it's a bit of an exploration problem amongst researchers just to explore these things. And that's exactly what we're finding here, is that introducing one element like these resets has sort of forced us to re-explore all of the rest of the hyperparameters, because the community consensus is just different. Like the old community consensus was no longer applicable. And so this series of papers that I described is essentially that, right? It's just the story of that exploration, redoing that exploration, and finding we can do actually much better than we previously could. I'm not sure if that answers your question, but okay.
And we've got one more on mic number 3, and then we'll have to wrap it up.
Well, thank you, Aaron. I think maybe you did just answer my question, which is, there's so many different things you looked at, and even different contexts and different experiments. It seems, one is left not clear what to think.
Yeah, that's fair.
Yeah, I guess that is right. Well, anyway.
So I guess I can say that this was essentially an exercise of having these resets and kind of running with them, right? Chasing, in a sense, chasing better performance, and then hoping that that will give us insights later on as to what we can do with that. I'm not sure. We've learned a few things. I still think we are slow to come to an understanding of why these things help. And I don't know if we're ever going to get there. We are sort of finding that there are contexts in which we don't need them. And so, I don't know. Maybe what we'll find is that these resets just sort of unlocked a quest for different kinds of strategies for learning out there, and then at the end of the day, they'll just disappear, and we won't necessarily really understand entirely why they worked. I mean, that's I would say probably the most likely scenario of this kind of work. Yeah.
So you'd agree that resets are not really an answer. They're a question. There's something that needs to be understood and figured out, and then.
Yeah.
And then the insight that we gain by understanding them might lead to a new algorithm.
That's right. I think what I think we're offering is just a sense of what's possible is slightly redefined now with these same basic algorithms, right? That's kind of the way I look at this. And I think that's useful, right? Because we now can, we might, at least in some respects, at least in this data efficient regime, we're in a different place than we were just, a year ago, based on that.
It's definitely useful and very interesting. Thank you, Aaron.
Thank you. All right, I think that's it. Thank you very much.